This is a lesson on total internal reflection in a unit on light and optics. We covered before that in a medium, light behaves differently than outside the medium. Each medium has an index of refraction which changes the speed of light in that medium. The wavelength changes, but the frequency doesn't. So we can see that it changes wavelength. And the path is altered by the law of refraction, also called Snell's law. An application of this Snell's law is total internal reflection, which means that when light travels from mediums of high index of refraction to low index of refraction, and so I might have water to air, and we're going upward here. There's an arrow here just to make sure the direction is imprinted in your head. We want to go from high to low. At that interface, a critical angle occurs where there's totally internal reflected light. So if I have light, some sort of incident ray, two things can happen at that interface. There's a reflected ray and there's a refracted ray. And this is a typical occurrence. There will be part of that light will go out and part of that light will stay in that material. As I keep increasing that angle here, you can see that based on Snell's law, this refracted ray out into the medium will keep moving closer and closer and closer to the interface of those two media. And that's the situation I have here at some sort of critical angle. It goes all the way to 90 degrees. Theta 2 goes all the way to 90 degrees. Within that, any light that it goes towards the surface and hits the surface is going to be totally internally reflected. For any angle within this, we're going to get refraction and reflection. Both can happen, but outside of it, it's going to be only reflection. Only reflection out here. So we have this special relationship happening. There's a 90-degree angle, and we have to have this specific relationship between the indices of refraction. So when we're calculating this, we bring up Snell's law. This is Snell's law, the law of reflection right there. We're going to note that theta 2 is 90 degrees, right? Theta 2 is 90 degrees, and we recognize sine 90 degrees as 1. So Snell's law simplifies to this very nice relationship. If I want to find this critical angle, beyond which is total internal reflection, I take N2 and divide by N1. And we're going to remember that N2 is always less than N1. This will always be a less dense material. We're always going from more dense to less dense. And so also I'm going to note down here, total internal reflection occurs for any angle greater than the critical angle. So any angle out here, you will have total internal reflection at this angle, and any angle outside of it will have total internal reflection. I've picked a quick example for us to work on this idea. Just use this equation here. It says determine the critical angle for total internal reflection in a diamond. And I put the index of refraction here for the diamond. We can see at the interface here, we don't care about those angles. We care that there's some sort of critical angle when it bounces off the bottom. And that comes with the special design of diamonds to reflect light back up and look sparkly. There's a very small critical angle here. It has a large index of refraction, and so there's going to be a small angle. So we can set this up. Sine theta c equals N2 over N1. We're going to note that N2 is for air, and N1 is for the diamond. Right? This is N1, and this is N2. N1 is the diamond, N2 is the air. So N2, we're going to put 1 up here. Well, you could put more significant figures, but it won't matter in your calculations. And then the N1 is 2.419. So when you solve this, a little bit of manipulation, you're going to use the inverse sine function in your calculator, the inverse sine, and you get theta c, the critical angle for diamond. The diamond air interface is 24.418 degrees. So that's that angle right here. For any angle outside of that, you will also get total internal reflection, but this is the minimum that meets total internal reflection. There's a few applications that I wanted to show you about total internal reflection. The first is dispersion and rainbows. When you combine those, dispersion happens with refraction for different wavelengths. And then when we get total internal reflection at the back of a raindrop, you can see that here, total internal reflection at the back of a raindrop, we get the formation of a rainbow. When you have a whole bunch of raindrops up in the air, you get a whole bunch of light, and you can see the difference between the red and the violet light and all of the spectra between. The angles of refraction and reflection for dispersed wavelengths become large enough for our human eyes to distinguish them. If they weren't large enough, the light would still be white light, and we would perceive it as white light. But when it gets large enough, we can distinguish those wavelengths, and we can see the red light separate from the orange or yellow or violet, etc. So here's a picture of that. You can see that you need a bunch of raindrops up in the atmosphere in order to get a cumulative effect. The lower raindrops will give you the lower wavelength light, and the higher raindrops will give you the higher wavelength light. So that's a very interesting effect. It's not magic. Once you know how this all works and you know the math of it, it's not magic. It's pretty cool. Another application I have in here, I mentioned before in the prior lesson, the fiber optics. A fiber optic cable is composed of a core, or the inside material, and we can see that here. There's a core, this inside material, and a cladding, which is the outside material. And so you take an inner material and an outer material, and you make their indices of refraction such that total internal reflection happens inside it, traps the light inside that cable. What you're seeing is that we're going to want the N2 in this situation less than N1. N1 will be a denser glass or plastic, and N2 will be a less dense glass or plastic. And once you've done that, once you set it up, you can see that you can transmit light along that fiber optic cable. I've chosen an example problem that deals with optical fibers. Constructing an optical fiber. It says an optical fiber uses flint glass clad with crown glass core. What is the critical angle? And I did pick this problem because I don't think they labeled N1 and N2 in here properly for you to be able to use this equation. If you set up the equation sine theta c equals some number over some number and it's greater than 1, that cannot happen. No, that cannot happen. Sine theta is always less than 1. Sine theta is always less than or equal to 1. So when you set up the ratio N2 over N1, you want to make sure N2 over N1 has to be less than 1. When I look at this situation, I want to look at total internal reflection at this interface here. I don't care what happens at the first interface. There will not be total internal reflection there because I'm going from a less dense material to a more dense material, and no total internal reflection will happen at this surface, at that first surface. It only happens up here at the second surface in order to keep this light ray trapped inside the core there. So when I look at this picture, inside is the core, so this is going to be crown glass inside here. And outside is going to be the flint. And I can properly identify N1 and N2 in here. N1 is the first material, which is crown glass, and N2 is the second material, which is flint glass. So I can look over here. Crown glass has 1.52 and flint glass has 1.66. So you may be getting the feeling I'm getting here when I set up this equation, sine theta c equals n2 over n1, I get 1.66 over 1.52. And I'm getting this situation where the sine theta c is greater than 1, and that's not possible. So what I would say on this problem is that they were trying to trick us. It's not possible to build fiber optic cable with crown glass inside and flint glass on the outside. You would need to choose something that has you would need a cladding, something on the outside that has an index of refraction less than crown glass rather than greater than. So watch the relationship of your indices of refraction there.